Hello, my name is Bill Kinney, and this is a very important video in my series about parametric curves. You can see it's part 21. It's a summary of the mathematical content in parts 1 through 20 in order to illustrate a very important concept that the velocity vector of a motion is the derivative of the position vector of the motion. We've been talking about vectors in some recent videos. I hope you've been hanging with me here. We've been focused on the same kind of example over and over and over again, just getting deeper and deeper into it. This video really is going to serve as a launching pad to do now lots of different kinds of examples here in parts to come. So stick with it. We are dealing with calculus, but if you're a pre-calculus student, I hope you can still get something out of it because we are focusing on the calculus from a very intuitive, physical, geometric perspective and trusting that Mathematica is calculating the derivatives for us, not worried about the technical details about why it works. So again, we're trying to illustrate that the velocity vector is the derivative of the position vector, just like the speed function is the derivative of the distance traveled function. Derivatives measure rates of change, how fast something is changing. So here's our summary. We've got our two main situations. In both cases, we're traveling from the point 2, -1 to the point -1, in 1 second, first at a constant speed, then at a non-constant speed. We have our basic parametric equations that we use to model this motion. We had two functions. F of t was -3t plus 2, and g of t was 4t minus 1. These two parametric equations, t is called the parameter, these are parametric equations, define the motion, they model the motion. We also thought about putting these together into a point-valued function that we called c of t by taking these things and making them the first and second coordinates of the point. So this is a moving point, a point-valued function. That was fairly easy. We got into non-constant motion then, and we created a function that we called h of t, which increases in value from 0 to 1 as t increases, as t increases from 0 to 1, just like the function h of t equals t does. This flexibility that we allowed in h of t allowed us to model non-constant speed motion. If h of t is concave up, that represents motion that increases in speed. If it's concave down, that represents motion that decreases in speed. If it's a mixture of concave up and concave down graphs that increase in value from 0 to 1 as t increases from 0 to 1, that's a speed that increases and decreases in value as we go. And we created a new parametrization that we created from C and H by substituting h of t into C, composition. If you figure out what that is for this example, it becomes -3 times h of t plus 2, 4 times h of t minus 1. And no matter what h of t is, as long as it's done this way, this still parameterizes the same line, possibly at different speeds, and possibly, if we allowed even further variability in h of t, it could start at a different place and end at a different place and that kind of thing. Alright, what did we do with this now? What we wanted to do was we wanted to create a distance function. A function, dist of t, that tells you how far you've gone after time t has elapsed. We used the Pythagorean theorem to figure out what it was, and it turns out we figured out that it was 5 times the h of t for this example. Then we relied on a calculus concept. We said the speed function is the derivative of the distance function, which graphically means the values of the speed graph give you the slopes of the distance graph. We're trusting Mathematica to do the calculation correctly, and it turns out that this ends up being 5 times h prime of t, where h prime of t is the derivative of h of t. the rate of change of h of t. The values of h prime of t give you the slopes of h of t. Again, I'm not specifying what h of t is. We also saw that the distance traveled up through, say, time b was the area under the speed curve. And again, thinking from a purely operational viewpoint without worrying about y, we said there's an integral symbol, a definite integral symbol, that represents the area under the speed graph. It's always above the horizontal axis. The area under the speed graph when t goes from 0 to b gives you the value of the distance traveled function. In some pretty recent videos, we introduced the idea of a position vector. We called it r of t. And essentially, it's the same as c of h of t, except we don't think of it as a point, we think of it as an arrow. And we use a slightly different notation. You can see here, it's a related but slightly different notation. Not everybody does this, but we're doing it. And in the very last video, part 20, we figured out, based on this, that the velocity vector, v of t, for this example, not in general, but for this example, is really the speed function times a particular constant vector that happens to have unit length. Here's this vector right here. First component, negative 3/5. Second component, 4/5. The vector whose first component is negative 3 and whose second component is positive 4 is an arrow that points from the point to negative 1 to the point negative 1, 3. By multiplying it by 1/5, we have rescaled it here to be a vector that has unit length, length 1. The norm of the vector is 1. By multiplying by the speed, we have created a vector that points in the right direction as the motion for this constant, well, for this motion along a straight line, and whose norm, whose length, is always equal to the speed because this one has unit length. This is a scalar, a number. Its value is equal to the norm, the length of the velocity vector. We're almost done here. What I claim is, the important fact here is that the derivative of the position vector is going to give us the velocity vector. First of all, for this example. Second of all, it will always work in general. The derivative of the position vector, r prime of t, is going to give you the velocity vector. Again, we're illustrating it with this example. This is not a proof. It's only an illustration with this example. But what I claim is that it's true always, as long as r of t, the position vector, is what's called a smooth function. As long as it's differentiable, this will always hold. Why does it work in this case? Well, you'd be trusting me when I say that we can differentiate r in this way. Certainly if you are in calculus, this should make sense. Remember, derivatives measure rates of change, how fast something is changing. The constant 2 doesn't change at all. Its derivative is 0, so it goes away. You don't see a 2 down here. Same with negative 1. It's a constant. Its rate of change is 0. It goes away when we differentiate. It turns out that these multiplicative constants, the negative 3 and the 4, just get carried along down here, and we can just multiply them times the derivative of the h, times h prime in each case. That number, that quantity, h prime, can be factored out. It is a number, it is a scalar that can be factored out of the vector, it turns out. And then through a little trickery, what we can do is we can factor out, so to speak, a 5 from the vector, even though you don't see a 5. Well, as long as we compensate by dividing the vector by 5, by multiplying it by 1/5, we can make it look like this. Now, compare this with this, and also this. If you do that comparison, since the speed of t is 5h prime of t, these two vectors are the same. This equals the velocity vector. It's true in this example. Based on how we've thought about it, we really defined the velocity vector in this way, in this example, and then you're trusting me that I can differentiate the position vector in this way and do this algebra. We verified that it equals this velocity vector that we defined. But what I claim is while this equation is not true in general, the fact that r prime of t, the derivative of the position vector, equals v of t, the velocity vector, is always true in general. That's the main thing we're going to use in some coming videos. And that's the end of this one.